Okay, this is a continuation of 5.4. There's a property that says if your logs, and you have one on them on each side, have matching bases, then their arguments are equal. This is analogy, kind of an analogy to the one we had where we said a to the u equals a to the v, so u equals v. Same thing's true here for logs that are set equal. As long as there's one on each side and their bases match, then their arguments are equal. So for example, this is a setup just like that. So we just set the answers equal. We solve it, so that would add up to 2x if we move it over. That would be negative 3. This is x to the negative 3/2. Unfortunately, you cannot just accept that this answer is correct. You could do that with exponentials, but logs have domain restrictions. So you have to make sure that each of these is going to be okay. You just set this part greater than 0 and solve it, and you do the same thing for this one. So this says negative x is greater than negative 1, so x is less than 1 because you divide by that. So it looks like for our domain in this equation, our answer has to be greater than negative 4, and at the same time it has to be less than 1. So negative 3/2 is negative 1.5, which fits in that situation. So this is okay. Another way to check this instead of doing the greater than 0 is just to plug this in and make sure. So if you plug your negative 3/2 into this, make sure that this comes out greater than 0. As long as that happens for both parts, you're okay. If it's greater than 0, it's a check. 1 minus x, 1 minus negative 3/2 is 1 plus 3/2, greater than 0, check. So instead of actually finding the full domain and writing it out like this, you could just check to make sure each part is greater than 0. You cannot have 0 in your argument or a negative. And that's based on, remember, the inverse functions and how domain and range are solved. So this one, again, 7 and 7 are both the same base, one on each side, so we set them equal. We would subtract over the x, so this equals negative 1. Notice that this case, x minus 5 being greater than 0 means we have to be greater than 5, and 6x being greater than 0 means that x has to be greater than 0. This negative 1 does not fit the bill. In fact, if you plug it back in, x minus 5 is negative 1 minus 5. That is negative 6. That is not greater than 0. And also it fails on the other side as well. This would be negative 6 as well. And you cannot have an argument that is negative. So we just can't do that in these cases, which means that there is no solution for part B. A lot of people don't see C as this situation, but it is two natural logs which are both base E, and they're on opposite sides, one on each side, so we set these equal. This would then be x squared equals 12 minus x. Move everything to one side by adding and subtracting. Factor, oop, that's not what I wanted to do, sorry. Let's back that up. There we go. I wanted to move this down. Okay. So when we factor this, this would be x plus 4, x minus 3. So that's x equals negative 4 or x equals 3. We have to check both solutions. So natural log of negative 4 squared equals natural log of 12 minus negative 4. As long as both arguments turn out positive or greater than 0, we're good. So this one is fine. Natural log of 3 squared equals natural log of 12 minus 3. This is 9, which is greater than 0. Both parts have to be greater than 0 for this to work. So both solutions work in this case. Now, where people get into trouble is then they get to these problems and they want to try to drop the log. Notice that this does not have a log on both sides. If you only have one log on one side, you can't drop the logs. You must convert to exponential. So 2 to the 4th equals this. So that would be 16 equals x minus 5. Add the 5 over. We think that x is 21. 21 minus 5 is definitely greater than 0. So we're good there. Let's look at the next one. So this would be 4 to the negative 3 halves equals x. Okay, negative 3 halves means that moves to the denominator. And then that is a radical. So that would be the square root of 4, and then we cube it. So that is 1 over 2 cubed, which is 1 over 8. And 1 over 8, since this is just an x, 1 over 8 is definitely greater than 0. So that is our solution. For f, this is log base 10. Notice they don't write it, but it's there. So 10 to the negative 4 equals x squared. We have to move that to the denominator. And 10 to the 4th was 10,000. You take a square root, and yes, normally we write plus or minus, and we have to check to make sure both answers work. This would be 1 over 100. And it would be plus or minus. And in this case, because this is being squared, 1 over 100 squared is positive, and negative 1 over 100 squared is also positive. So we're good on both. So both of these would be solutions. This is, notice we have e hidden there. But there's this negative power, so you might want to move that up first. This is e to the, oh, we don't know that rule yet. Sorry, I'm jumping ahead. We could write this as a log version. That might help here. So log of base, exponent goes on the other side. Argument is the piece that was on the right of this exponential. This is natural log as well, and that means that we can, well, we can't drop the logs essentially because we have that negative 1 there. I think we need to save this guy. We need fancy property from 5.5, 5.6 that we haven't learned yet. So just omit. This one can be solved, but we need a different property. Okay, and then radioactive isotopes again. So radioactive iodine 131 is frequently used in tracer studies involving the thyroid gland. This is the formula they give you. A sub 0 is the initial dose, T is the time in days. Find A assuming that the half-life is 8 days. Now, what you have to remember about the half-life, that means that whatever you start with, you have half of that at the end. So this is A sub T if you're doing half-life. This is A to the negative 8. So we can actually divide the A sub 0 out because we don't care how much we started with, we just want to know that we have half left over. Now to solve this, I would move that down and make it in a denominator. Then I would cross multiply. 2 times 1 is just 2. And then we can use our property about taking a root. Now normally we would write a plus or minus because it's an even root, but you do not want a negative answer for the power that you're using here, or the base. So this is 1/8. So 2 to the 1 divided by 8 power is I don't know if that actually did that for me. Hang on. 2 to the 1 divided by 8 power is 1.09. So our original base should have been 1.09. Now usually we don't make you do this version. I'm just letting you know so you don't stress out. We usually give you something that we give you all the information you plug in. This one's a little vague because you have to realize that half-life just means the a sub 0 part is kind of null. We don't need it. Okay, so 11 and 12 are our last two examples. So we're almost done with this section. And remember we said we would spend some time on this on Monday when we get back after Thanksgiving. So the population N of T in millions of the United States T years after 1980 may be approximated by this formula. When will the population be twice what it was in 1980? So twice 1980 would be 462. If we divide this over, because we're trying to get the E by itself, that would just be 2 equals all of this. And now we're at our first time where logs are actually important. If your variable is in an exponent, a log can fix that. And I'm specifically going to use the natural log because this is base E. So if I write this, this is log base. The exponent goes on the other side, and the argument goes here. This becomes natural log because that's how we actually write that. And now, because our calculator has a natural log button, if we divide this decimal over, we can solve this problem. So we take our calculator, we do 2 to the natural log, and sometimes again you have to hit natural log first, sometimes you hit 2 first. You have to check your calculator, but it should give you 0.69314 blah blah blah. And then we're going to divide that by the 0.0103, and that gives us approximately 67.3. So it'll be about 67.3 years for them to double their population. And if they want a specific answer for that, we could just say 67 years. So 1980 plus 67 is 2047. That will be when they double their population. Okay, this one is another application of compounding continuously, which remember is our PERT formula. We have a rate of 0.06. We want to know the number of years, so we don't know T. We have initial deposit of 6,000 and we want 25,000. So 25,000 equals 6,000 e to the 0.06 T. I would divide the 6,000 over first, get the E by itself, because you're going to end up using a log since this has a T and a exponent. You can cancel out 3 zeros, so this is just 25 over 6. I wouldn't turn it to a decimal yet. This is e to the 0.06 T. Then we're going to take, we're going to take this and turn it into a log to get that T out of that exponent. So log, remember you use base, argument, exponent. So base is E, exponent goes over here, argument is the answer from the other part. And this would be natural log of 25 over 6, because it's log E, equals 0.06 T. We just need to divide by the 0.06 to get our approximation for the number of years. So 25 divided by 6 is my number. I'm going to take a natural log of that and divide by 0.06. So 23.8. If you want to round up to a whole number, approximately 24 years. So you'd have to let if you have a continuous compounding account at 6% interest and you put an initial deposit of $6,000 down, in about 24 years you will have $25,000 in that account. This one's actually very useful for your real life, especially if you're wanting to save for retirement. So that is the end of section 5.4.